Hello everyone, my name is Mohammed Arif AIIMS. So, in the last class, we discussed organic compounds containing oxygen, the first part of the lecture of the chapter alcohols, phenols, and ethers. So, today we'll be discussing the second part of that. The chapter we are discussing is aldehydes, ketones, and carboxylic acids. In aldehydes, the carbonyl group is bonded to a carbon and hydrogen, while in the ketones, it is bonded to two carbon atoms. So, an aldehyde group we represent it by RC double bond O. You can see the carbon is bonded to a hydrogen and oxygen atom. While in ketone group, the carbon is attached to oxygen and to other carbon atoms of the alkyl groups. The carbonyl carbon in which carbonyl group is bonded to carbon or hydrogen and oxygen of hydroxyl moiety are known as carboxylic acids. While in compounds where carbon is attached to carbon or hydrogen and nitrogen of NH2 moiety or to halogens are called amides and acyl halides respectively. So, if the carbon atom is attached to an oxygen and a hydroxyl group, it's called a carboxylic acid. That's what it's essentially telling. And if it is attached to oxygen and NH2 group, we get an amide. And if it is attached to oxygen and a halogen, it's called a acyl halide, sorry. Depending on which halogen it is, we call the suitable name. If it is chlorine atom, we call it as acyl chloride, etc. Okay, now esters and anhydrides are derivatives of carboxylic acid. So, what are esters and anhydrides? What are esters? Esters mean a carboxylic acid reacts with an alcohol. So, can eliminate O's from here and H from here. So, we will get an ester will not by RCOO R dash. It's an ester. So, what's an anhydride? It's a condensation product of two carboxylic acid. So, we will get RCOO. Or we can simply denote it as RCO is called acid anhydride. So we have given the general structure of all these compounds here. Now we'll move on to nomenclature of aldehydes and ketones. Aldehydes and ketones are often called by their common names instead of IUPAC names. The common names of most aldehydes are derived from the common names of the corresponding carboxylic acids by replacing the ending ic acid of acid with aldehyde. So, how do we tell the common names of most aldehydes and ketones? We simply say the common name of the acid and replace the IC of acid with the name aldehyde. So here we know this is acetic acid CH3CHO. We simply change the IC acid, the term IC acid from the name, and we added the term aldehyde. So we get the name acetaldehyde. Here similarly we know this is, if COH group was present instead of CHO, this would be benzoic acid. So we simply remove the term oic acid from the name and add the term aldehyde. So we get benzaldehyde. Okay. The location of the substituent in the carbon chain is indicated by Greek letters alpha, beta, gamma, delta. So this is for common names. Okay. The alpha carbon being the one directly linked to the aldehyde group, beta. So in writing the common names, the position of the carbon atom attached to it is denoted by the carbon atom directly attached to the carbonyl group. We tell it is the alpha carbon, and the next carbon will be beta carbon, and the next one will be gamma carbon. Okay. The common names of ketones are derived by naming two alkyl or aryl groups bonded to the carbonyl group. The location of substituents are indicated by Greek letters alpha, alpha dash, beta, beta dash, so on, beginning with the carbon atoms next to the carbonyl group, indicated as alpha, alpha dash. So for ketones, we simply say the common names of both the groups on either side of the CO group. So here is known as acetone. This compound is known as acetophenone. Similarly, here it is propylphenol. So how do we decide which is the alpha carbon, beta carbon atom? For example, in ketones, if we denote one carbon as alpha, the opposite side carbon will be alpha dash. So here also alpha, alpha dash will be alpha, alpha dash, beta, beta dash. Similarly, we can name the carbon compounds or show the position of the carbon compounds. The UPC names of open chain aliphatic aldehydes and ketones are derived from the names of the corresponding alkenes by replacing the ending E with al, and also you can simply take one example. We will take a aldehyde and a ketone. We have acetaldehyde and acetone here. So how do we name this according to a UPC system? So we first simply take the carbon chain, long as carbon chain, and write the name considering there is no carbonyl group. So this will be what? This is a two carbon chain. So it will be ethane, right? And this will be propane because there is three carbon. And we remove the ending E from the name. And for aldehyde, we add the term al, and for ketone, we add the term ol. So for ketone, the oxygen atom is in the second carbon, and for aldehyde, it will be in the first carbon. So we number it accordingly and add it to the name. So this is how we name carbonyl compounds in IUPAC system. In case of aldehydes, the longest carbon chain is numbered starting from the carbon of the aldehyde group, while in case of ketones, the numbering begins from the end nearer to the carbonyl group. So aldehyde groups are always at the ends. So we take it as first group there. For ketones, so imagine this is, we'll draw another ketone to make the concept clear. We know C2H5 COCH3. So in this we can number, we may draw the diagram of this compound. It will be like CH3, CH2, C double bond O, CH3. So we can start numbering the compound from both the sides. Like we can start from 1, 2, 3, 4 here, and also from the other end 1, 2, 3, 4. So we should be numbering in such a way that the carbonyl carbon gets the lowest number. So this second way of numbering will be the correct order. So when we name the compound, the name will be for butane 2 on. Sorry here, it was a small mistake. It is butane 2 on. Okay. Now The substituents are prefixed in alphabetical order along with numericals indicating their position. If there is substituents present in the chain, we show that in the name by giving the number to the appropriate carbon and showing the number in the name. The same applies to cyclic ketones where the carbon is numbered 1. And the aldehyde group is attached to a ring. The suffix carbaldehyde is added up to the full name of the cycloalkane. Aromatic aldehydes are named as substituted benzaldehyde. So we'll all see this with examples right now. So in this cycloalkane here, we can see that the CHO group is attached to a ring. So for naming this compound, we simply add the name what carbaldehyde to the end of the name. So here you can see carbaldehyde is added to the name. So when we number it, how it will be numbered? We number it from 1, 2, 3. So we number it this way. So the substituents also get the lowest number here. So in third position there is a methyl group. So 3-methyl cyclohexane carbaldehyde will be the APS of this compound. Similarly, in aromatic compounds also, if CH group is attached, we add the term carbaldehyde. So here we can have the name benzene 1,2 dicarbaldehyde. So that's all there is for nomenclature of the compounds. Now structure of the carbonyl group. The carbonyl carbon atom is sp2 hybridized and forms 3 sigma bonds. The fourth valence electron of carbon remains in its p orbital and form a pi bond with oxygen by overlap with p orbital of an oxygen atom. So CO group, carbonyl group, you can see RC bond O H. So it forms 3 sigma bonds. It is an aldehyde. It forms sigma bond with alkyl group, hydrogen, and oxygen. 3 sigma bonds, and it forms 1 pi bond with the oxygen atom here. So you can see that the 3 sigma bonds are in one plane here, and the pi bond is present above and below this plane. In addition, the oxygen atom also has 2 non-bonding electron pairs, just the carbonyl carbon, and 3 atoms attached to lie in the same plane, and the p electron cloud is above and below this plane. So you can see that both the 3 sigma bonds are in one plane, and the pi bond is going above and below this plane. P electrons are above this plane. The bond angles are approximately 120 degrees because what is a trigonal coplanar structure. The carbon oxygen double bond is polarized due to higher electronegativity of oxygen relative to carbon. So we know oxygen is more electronegative than carbon. So the bond is more polarized towards oxygen. Hence the carbonyl carbon is an electrophile or Lewis acid, and the carbonyl oxygen is nucleophilic or Lewis base center. So the carbon acts as a Lewis acid and oxygen acts as a Lewis base center. Now we will go to preparation of aldehydes and ketones. The first method is by oxidation of alcohols. So in presence of strong oxidizing agents, what alcohols are directly oxidized into carboxylic acid. So for preparation of aldehydes and ketones, we use mild oxidizing agents such as CrO3, chromium oxide, or pyridinium chlorochromate (PCC). So primary alcohols are oxidized to aldehydes, and secondary alcohols are oxidized to corresponding ketones. Second method is by dehydrogenation of alcohols. So this method is suitable for volatile alcohols and is of industrial application. In this method, alcohol vapors are passed over heavy metal catalysts. Primary and secondary alcohols give aldehydes and ketones respectively. So this method is known as catalytic dehydrogenation. So we pass the volatile alcohol in the presence of a catalyst through a catalyst at 573 Kelvin, and we get the corresponding alcohol, aldehyde or ketone. So if it is a primary alcohol, we get the aldehyde, and secondary alcohol, we get the ketone. Same as before. And third method is from hydrocarbons. So first one is what? Ozonolysis of alkenes. By ozonolysis of alkenes. As we know, ozonolysis of alkenes followed by reaction with the zinc dust and water gives aldehydes, ketones, or a mixture of both, depending on the substitution pattern of the alkene. So simply think of this reaction. Ozonolysis is what? We add ozone and reduce using zinc. Simply think that the bond is cleaved here and the double bond O is added at both the ends. So we get such a compound. So in this side, if it is a hydrogen and an alkyl group here, we will get an aldehyde. Or if there is both alkyl groups present here, what we will get a ketone. So depending on what is present, we will get the product accordingly to that. Second method is by hydration of alkanes. Reaction of water to ethane in the presence of H2SO4 or HgSO4 gives acetaldehyde. All other alkanes give ketones in this reaction. So we are hydrolyzing alkane in presence of H2SO4 or HgSO4, and we will get aldehyde or ketone, but only ethane gives aldehyde. All other compounds give what? Ketones. So we'll write the reaction here. So we hydrolyze it. What do we get? We get the corresponding aldehyde. So only ethane will give an aldehyde. So that's all you should know about this reaction. Now, preparation of aldehydes. So we talked about some common methods until now for both aldehydes and ketones. Now we'll see methods exclusively for aldehydes. So first method of preparation is from acyl chloride. Acyl chloride or acid chloride is hydrogenated over catalyst, palladium or barium sulfate. This reaction is called Rosenman reduction. So when we react in acyl chloride with hydrogen presence of palladium barium sulfate, we will get the corresponding aldehyde. So here benzoyl chloride we are reacting and we get benzaldehyde. So this reaction is what is known as Rosenman reduction. Hydrogen in palladium barium sulfate. Now the second method is from nitriles and esters. Nitriles are reduced to corresponding imine with stannous chloride in the presence of HCl, which on hydrolysis gives corresponding aldehyde. This reaction is called Stephen reaction. So what is happening? We are reacting nitrile with SnCl to HCl and we get the corresponding imine. When we hydrolyze it, we get the aldehyde. This reaction is known as Stephen reaction. Alternatively, nitriles are selectively reduced by diisobutyl aluminum hydride, or we simply call it as DiBALH, to imines, followed by hydrolysis to aldehyde. So here also same thing is happening. We will get the corresponding imine, and when we hydrolyze it, we get the aldehyde. The point to note is this reaction does not affect double bonds. So we can see the second reaction. The double bond is not affected while producing the product. Esters are also reduced to aldehydes with dibyl. So we can also reduce esters with the help of dibyls to the corresponding aldehydes. Now, third method is from hydrocarbons. Aromatic aldehydes are prepared from aromatic hydrocarbons by the following methods. So, first, we use methyl benzene, or we simply call it as toluene. So, the reagent we are using here is chromium chloride, chromyl chloride, CrO2, Cl2. Chromium chloride oxidizes methyl group to chromium complex, which on hydrolysis gives corresponding benzaldehyde. So, this reaction is known as Pitat reaction. Okay, so, we have learned three named reactions until now: Rosen reduction, Stephen reaction, and Pitat reaction so far now. So, toluene, when we react with chromium chloride, we get the corresponding benzaldehyde on hydrolysis. Use of chromic oxide or CrO3. Toluene or substituted toluene is converted to benzylidene diacetyl on treating with chromic oxide in acetic anhydride. The benzylidene diacetyl can be hydrolyzed to corresponding benzaldehyde with aqueous acid. So, we are reacting toluene or substituted toluene with chromium oxide and acetic anhydride, and we do hydrolysis. We get benzaldehyde is the product. Second method is by side chain chlorination followed by hydrolysis. Side chain chlorination of toluene gives benzyl chloride, which on hydrolysis gives benzaldehyde. So here, free radical halogenation is happening. Toluene, we are reacting with Cl2, presence of light, we get benzyl chloride. So on hydrolysis, what's happening here? We are getting two OH group in place of Cl, and the water is eliminated. And so we get CH2 group. So that's how we get the product. Now by Gattermann-Koch reaction. When benzene or its derivatives treated with carbon monoxide and hydrogen fluoride in the presence of anhydrous aluminum chloride or cuprous chloride, it gives benzaldehyde or substituted benzaldehyde. So we are reacting benzene with COHC in presence of anhydrous aluminum chloride or cuprous chloride, and we will get the aldehyde here, benzaldehyde. So this reaction is known as Gattermann-Koch reaction. Now we will see preparation methods of ketones. The first method is from acyl chloride. Treatment of acyl chloride with dialkyl cadmium prepared by the reaction of cadmium chloride with Grignard reagent. So when we react cadmium chloride CdCl2 with Grignard reagent, we get dialkyl cadmium, and we react this dialkyl cadmium with our acyl chloride, and so the alkyl group is inserted into this acyl chloride in place of the halogen, and we get the corresponding ketone there. Okay. Now the second method is from nitriles. Treating a nitrile with Grignard reagent followed by hydrolysis yields a ketone. So nitrile we are reacting with a Grignard reagent. So we have here CH MgBr. Presence of either what we know the bond shifts here. Nitrogen is more electronegative than carbon, so be negative, will be positive. MgBr will be positive and CH will be negative. So this attacks this carbon atom and MgBr attacks the nitrogen atom, and we get this product. So we are hydrolyzing this product and we get the corresponding ketone here. Okay. Now from benzene or substituted benzenes. When benzene or substituted benzene is treated with acid chloride in presence of anhydrous aluminum chloride. So we know this, we have seen this reagent before. This is called as what? Little-Crafts reaction. Little-Crafts acylation reaction. So what happens? We get the corresponding ketone there. Now we will we'll see some physical properties of aldehydes and ketones. The boiling points of aldehydes and ketones are higher than hydrocarbons and ethers of comparable molecular masses. It is due to weak molecular association aldehydes and ketones arising out of dipole-dipole interaction. So we know that in carbonyl group the trio bond is polarized. So due to this polarization, there is weak interaction, and so their boiling point is higher than the normal hydrocarbons of comparable molecular mass. Also, their boiling points are lower than that of alcohols of similar molecular masses. So we know in alcohol there is hydrogen bonding present. So obviously their boiling point will be higher than aldehydes and ketones. So we have seen the given here the boiling point of normal alkane, either ketone and alcohols, and we have given their boiling points here. So we can see highest is for alcohol here. The lower numbers of aldehydes and ketones such as methanol, ethanol, and propanol are miscible with water in all proportions because they form hydrogen bond with water. So the lower members are miscible in water because they form hydrogen bond in water. However, the solubility of aldehydes and ketones decrease rapidly and increasing the length of alkyl. So as the length of alkyl chain increases, the miscibility will decrease because we know the alkyl group is hydrophobic in nature. All aldehydes and ketones are fairly soluble in organic solids. So they are all soluble in organic solvents such as benzene, ether, methanol, chloroform, etc. The lower aldehydes have sharp, pungent odors. As the size of the molecule increases, the odor becomes less pungent and more fragrant. So lower aldehydes are having sharp, pungent odors. So as the size of the carbon chain increases, the smell becomes more fragrant. Now we will see some chemical reactions of aldehydes and ketones. First will be nucleophilic addition reaction. Aldehydes are generally more reactive than ketones in nucleophilic addition due to their steric and electrons. So aldehydes are more reactive than ketones. Addition of HCN or hydrogen cyanide. Aldehydes and ketones react with hydrogen cyanide to yield cyanohydrins. So we know carbonyl group is polarized. Oxygen will have slight negative charge, carbon will have positive charge. So the CN group will attack the carbon group, and we will get a tetrahedral intermediate here. And the final product will be cyanohydrin. A CN group and a OH group is attached to the carbon here. So the group is not called as cyanohydrin. Second reaction is addition of hydrogen sulfide. Sodium hydrogen sulfide adds to aldehydes and ketones to form the addition products. So here also same only. You know, we get minus charge here, carbon will be positive charge, and NaHO3, Na will be plus charge, HSO3 will be negative charge. So we will get the product as like this here. Over there is an exchange that happens here between hydrogen and sodium here, and we get this product. This product is known as what is known as bisulfate addition compound, but due to proton transfer. Now addition of Grignard reagent. So just keep in mind that we only get a primary alcohol when we add Grignard reagent to formaldehyde. Rest all reactions will be getting either a secondary alcohol or a tertiary alcohol. So if we add Grignard reagent to other aldehydes, except formaldehyde, we get a secondary alcohol. And if we add Grignard reagent to a ketone, we get a tertiary alcohol. Addition of alcohols. Aldehydes react with one equivalent of monohydric alcohol in the presence of dihydrogen chloride to yield alkoxy alcohol intermediate known as hemiacetal. So aldehydes react with alcohols in presence of HCl gas. What we will get? Hemiacetal product, which reacts with one more molecule of alcohol. So this again reacts with one more molecule of alcohol, and we get the product acetal here. Ketones react with ethylene glycol under similar conditions to form cyclic products known as ethylene glycol ketones. So ketones will react with ethylene glycol to form what? Ethylene glycol ketones. So we can see there is a ring present here. Okay. Now acetals and ketones are hydrolyzed with aqueous mineral acids to yield corresponding aldehydes and ketones. So when we hydrolyze these acetals and ketones, we get the corresponding aldehyde or ketone there. Now addition of ammonia and its derivatives. Nucleophiles such as ammonia and its derivatives, we denote it as NH2. NH2 is that. If the Z is a hydrogen, we call the group as ammonia. So we can see here what are the products forming here. So this is the general formula of the reaction here. So the CO group reacts with ammonia as derivatives to form these products here. So depending upon the product, we have different names for the products. If it is H, we know the reagent is ammonia. Product name will be imine. If it is an alkyl group, known as amine, we will get a substituted imine or known as Schiff base. If it is an OH group, we get oxime. NH2 group, we get hydrazone. NHCCSO, we get phenyl hydrazone. And if we have 2,4-dinitrophenyl hydrazine, we get 2,4-dinitrophenyl hydrazone. If it is a semi-carbazide, we get semi-carbazone. So the names are also very important here. Second reaction is reduction. Reduction to alcohols. Aldehydes and ketones are reduced to primary and secondary alcohols respectively by sodium borohydride or lithium aluminum hydroxide by catalytic hydrogenation. So aldehyde we are reducing by any of these methods, either by lithium aluminum hydride or sodium borohydride or by catalytic hydrogenation. What we are getting? We are getting corresponding primary alcohol here. Or if we are reducing a ketone, we get what? We get the secondary alcohol as the product. Now reduction to hydrocarbons. The carbonyl group of aldehydes and ketones is reduced to CH2 group on reacting with the zinc amalgam and concentrate HCl. So zinc amalgam concentrate HCl. We are reacting CO group. It gets reduced to CO group gets reduced to CH2 group. This reduction is known as Clemmensen reduction. Or alternatively, we can react it with hydrazine and then heating it with KOH or ethylene glycol. There also we are reducing the CO group to CH2 group. So this reduction is known as Wolff-Kishner reduction. Third oxidation. Aldehydes are easily oxidized to carboxylic acids on treatment with common oxidizing agents like nitric acid. So if you are using common oxidizing like strong oxidizing agents, nitric acid, KMnO4, A2CR2 or 7 and all, will directly oxidize the aldehydes to carboxylic acid. Ketones are generally oxidized under vigorous conditions. That is, we need strong oxidizing agents here and at elevated temperatures. Their oxidation involves carbon-carbon bond cleavage. So here also we will get carboxylic acid, but the chain length will be lesser than the parent ketone there. So here you can see here if you are cleavage of this bond within the first and second carbon here, we get the product as what? RCH and RCH2 CH. So depending upon the where this cleavage is happening, we'll get two sets of products here. So that is a point to be noted here. Or we can either here leave here. So we'll get another set of products here. The mild oxidizing agents given below are used to distinguish aldehydes from ketones. So we use different tests to distinguish between aldehydes and ketones. So tolerance test. What tolerance test? We add tolerance reagent, which is ammoniacal silver nitrate solution, and we'll get a bright silver mirror. because of the formation of silver metal here. This is what is tolerance test. Now, second test is fillings test. In fillings test, what we mix equal volumes of filling solution A and filling solution B. So, what is filling solution A and filling solution B? Filling solution A is, of course, copper sulfate. Filling solution B is alkaline sodium potassium tartrate. So, we mix this in equal proportion and add it to our organic compound present. So, if it is an aldehyde, we will get what? We get red brown precipitate. Ketones do not give this reaction. But you should also note that aromatic aldehydes do not respond to this test. Okay. The third test is halogen reaction. Aldehydes and ketones having at least one methyl group linked to the carbonyl carbon. So the condition is there should be at least one methyl group at the end of the compound. So in ketones here, we have here CH3 group attached to the CO group at the end. So we are reacting it with sodium hypohalate to form the corresponding. So in this reaction, we are getting this haloform. So that will give the reaction here. Now, fourth will be reaction due to alpha hydrogen. So what is alpha hydrogen? The hydrogen attached to the alpha carbon. The first reaction we have to learn about is aldol condensation. So here what is happening? Aldehydes and ketones having at least one alpha hydrogen undergo a reaction in the presence of dilute alkali as well as a catalyst to form beta hydroxyaldehydes or aldol or beta hydroxy ketones, ketone. This is known as aldol condensation. The aldol and ketone readily lose water to give alpha beta unsaturated carbonyl compounds. So we will take this for an example with, we'll take acetaldehyde. So in order two of this compound will react. So when we take this compound, we'll write it as first one compound we should write like this. The other compound we should show the alpha hydrogen separately for that. To form the product, we will simply polarize the CO bond. Oxygen will have a negative charge, carbon will get positive charge. Here also same. This bond will be shifted here. So carbon will get negative charge, hydrogen will get positive charge. And this hydrogen will go and react with this negatively charged oxygen, and this negatively charged carbon will attach to positively charged carbon here. So we'll get the product as what? CH3, C, CH, CH2, OH, CHO. And what happens next? Next, we lose a water molecule and we'll form a double bond. And we'll get what? CH3, CH, double bond CH, CH. So this is how you can do it with this any compound. Now what is cross alveolar condensation? So in alveolar condensation, we reacted two of the same compound, but here we react two different compounds, two different aldehydes here. So we can see here we have what? Ethanol and propanol. So here we will get what? Two sets of products because the reaction can happen two ways. So we'll get two sets of products here. Try and write and see the products yourselves. Now the reactions, Cannizzaro reaction. Aldehydes which do not have an alpha hydrogen. So aldehydes which do not have an alpha hydrogen atom. Example, formaldehyde. It will undergo self-oxidation and reduction. It is known as what? Disproportionation. So when we think of Fenner arrow, here is a disproportional reaction. So we'll get what? One aldehyde will be oxidized to acid and one will be reduced to alcohol. So we'll get methanol and potassium salt of acid. That's what is happening here. Now, electrophilic substitution reaction. Aromatic aldehydes and ketones undergo electrophilic substitution, the ring in which the carbonyl group acts as a deactivating and metadirecting. So, carbonyl group is what is a deactivating group or electron withdrawing group. So, we'll get the meta product. So, here we are doing nitration and we got the meta nitro product here. Now, we will discuss about carboxylic acids. We already discussed what is carboxylic acid. There will be a carbonyl group and this carbon group is also attached to a hydroxy group. The nomenclature of carboxylic acid. The common names end with the suffix oic acid and have been derived from Latin or Greek name of their natural source. So many of the carboxylic acids have the common names because of the sources from which it is derived from. For example, formic acid, what it was first obtained from red ants. So red ants are known as what? Formica indica. Acetic acid from vinegar. Butyric acid from rancid butter. In the IUPAC system, aliphatic carboxylic acids are named by replacing the ending E in the name of the corresponding alkane with oic acid. So similar to what we did with aldehydes. Do you know? CH3 is ethane. So CH3 COH is ethane, and we remove the E and add the term oic acid. And we will get the IUPAC. For naming compounds containing more than one carboxyl group, the alkyl chain leaving carboxyl group is numbered. And the number of carboxyl group is indicated by adding the multiplicative prefix dicarboxylic acid, tricarboxylic acid, etc. to the name of the parent alkyl chain. So if there is more than one COH group present, so we will see an example here. So here we have this compound. So we'll just write it to the side. So now we have seen in this compound there is more than one COH group. So what we do? We number the parent carbon chain. How? Excluding the COH group. So here we can either number start from right to left or left to right, because it's a symmetrical compound here. So we number it like that, and then how we write the name? Pro and 1, 2, 3 carboxylic acid. That's how we name the compound if there is more than one COH present. So here in this compound we can see that there is two COH group attached to the benzene ring. So the name will be benzene 1,2-dicarboxylic acid. Okay, now we'll see the preparation of carboxylic acid from first method is from primary alcohols and aldehydes. So we have already seen that by simply oxidizing we get the corresponding carboxylic acid. So here we are using what alkaline came for it is a strong oxidizing agent. We get the corresponding carboxylic acid, or we can use the CrO3H2, which is known as Jones reagent, and we will get the corresponding carboxylic acid here also from alkyl benzenes. Aromatic carboxylic acids can be prepared by vigorous oxidation of alkyl benzenes with chromic acid or acidic or alkaline potassium permanganate. We can use chromic acid or acidic or alkaline potassium permanganate, so strong oxidizing agent. So the point to be noted here is that no matter what the length of the alkali group attached to the benzene ring is, we always get what? Always get benzoic acid of the product there. So even if it is CH3 or CH2, CH2, CH3, we get the same product, benzoic acid there. From nitriles and amides. Nitriles are hydrolyzed to amides and then to acids in the presence of H plus or OH minus catalyst. Mild reaction conditions are used to stop the reaction that amides. So you can simply hydrolyze nitriles to carboxylic acid. So if you use mild conditions, mild acid or mild base, we can stop the reaction at the amide stage. That's what it is telling. Now from Grignard reagents. Grignard reagents react with CO2 to form salts of carboxylic acid, which in turn give corresponding carboxylic acids after acidification with mineral acid. So Grignard reagent react with CO2 in presence of dry ether. When we hydrolyze it, we get the corresponding carboxylic acid there. So what to note is that the carboxylic acid formed is having one carbon more than the parent alkyl group there. Now from acyl halides and anhydrides. Acyl chlorides when hydrolyzed with water give carboxylic acid, or more readily hydrolyzed with aqueous base to give carboxylate ions, which on acidification provide corresponding carboxylic acid. So we can react with either with what acid or base, acidic or alkaline hydrolysis. So acidic hydrolysis we simply get carboxylic acid, but basic hydrolysis we easily get the product, but it will be a salt, methyl salt there. So we can hydrolyze this methyl salt again to form the carboxylic acid. Benzoic anhydride. Anhydrides also are hydrolyzed to corresponding acids there. Now from esters. Acidic hydrolysis of esters give directly the carboxylic acid, while basic hydrolysis give here also same acidic hydrolysis we get the corresponding acid and alcohol. If it is basic hydrolysis, we will get first a metal salt there, and then when we hydrolyze it, we get the acid there. Now physical properties. Aliphatic carboxylic acid up to 9 carbon atoms are colorless liquids at room temperature. Okay, so lower members are what? Colorless liquids. Higher members are wax-like solids. So carboxylic acids have higher boiling liquids than aldehydes, ketones, and even alcohol. So they are higher boiling compounds, even more than alcohols, because what? Because of hydrogen bonding. This is due to more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. So as carboxylic acids are bonded to each other through hydrogen bonding. Hydrogen bonds are not broken completely. So in vapor state, they exist as dimers due to hydrogen bonding. Simple aliphatic carboxylic acid up to 4 carbon atoms are miscible in water due to formation of hydrogen bonds. So up to 4 carbon atoms, carboxylic acids are miscible in water because of hydrogen bond. The solubility decreases with increasing number of carbon atoms. We know the reason because of the increasing size of the hydrophobic alkyl chain. Benzoic acid is the simplest aromatic carboxylic acid. It is nearly insoluble in cold water. Carboxylic acid are also soluble in less polar organic solvents like benzene, ether, alcohol, chloroform, etc. Okay, now we will see some chemical reactions. Reactions involving cleavage of OH bond. So first will be reaction with methyls and alkalis. Carboxylic acid alcohols like alcohols evolve hydrogen with electroposition. So we have already learned the acidic nature of alcohols thereby reacting it with metals there. We evolve hydrogen gas there. However, unlike phenols, they react with weaker base. So they also react with weaker bases such as carbonates and hydrogen carbonates to evolve carbon dioxide. So hydrogen carbonate, what they evolve CO2. So this is a test used for detection of carboxylic acid group in the organic compound. Carboxylic acids are weaker than mineral acids, but they are stronger than alcohols and many simple things. So carboxylic acids are weaker than mineral acids, but they are stronger than alcohol. So we can be seen through their pK values. pK value of hydrochloric acid is -7. But trifluoroacetic acid, which is the strongest carboxylic acid, pK value of trifluoroacetic acid is 0.23. Benzoic acid is 4.19 and acetic acid is 4.76. So now the acidic strength of carboxylic acid. Electron withdrawing group got increase the acidity of carboxylic acid, and electron donating groups decrease the acidic strength. So the electron withdrawing, the strength of the groups are attached to the carboxylic acid. So CF3 will have the strongest electron withdrawing power, and phenyl group will have the most less. And we have arranged here the carboxylic acid according to their pK value. So CF3 serves the strongest carboxylic acid. So we will see the effect of an electron withdrawing group in benzoic acid. We know CH3 is an electron donating group, and NO2 is an electron withdrawing group. So their pK value 3.41, 4.46, 4.1. So this will be most acidic, this will be least acidic. Now reactions involving cleavage of COH bond. First is formation of anhydride. So 2 moles of any acid what non-heating with mineral acids give corresponding anhydride. Acidification reaction, what an acid and an alcohol react by elimination of water molecule, we get a ester there. Now PCl5, PCl3, SOCl2 and all. What happens? The halogen atom replaces the OH group present there, and you get the acid chloride as a product. And to notice, reaction with SOCl2 is preferred because the byproducts formed are escapable gases. So we will get the pure product here. Now reaction with ammonia. Carboxylic acid react with ammonia to give ammonium salt, which on further heating at high temperature give amide. So we react with ammonia and heated, we will get the corresponding amides here. Here we get this is phthalimide. Phthalimide on heating, what we get? We get phthalimide. So very important reaction here. Phthalimide on heating, we'll get phthalimide. Now reactions involving COH group. Reduction. Carboxylic acids are reduced to primary alcohols by lithium aluminum hydride or better with diborane. Diborane does not easily reduce functional groups such as ester, nitro, halo. So carboxylic acids on reduction with lithium aluminum diborane, we get the corresponding alcohol. But the point to be noted is we cannot reduce carboxylic acid with sodium borohydride. Okay, now moving on to decarboxylation. Carboxylic acid lose carbon dioxide to form hydrocarbons when their sodium salts are heated with soda lime. What is soda lime? Soda lime is NaOH and CO in the ratio of 3:1. So when we react the sodium salt of carboxylic acid with soda lime, we get the corresponding alkane with 1 carbon less. So 1 carbon less. Can produce alkanes from carboxylic acid also with what? Through Hobbes electrolysis. It is discussed in another chapter, but you should know that through the hydrocarbon prepared through Hobbes electrolysis, we have what? We have twice the number of carbon atoms present in the alkyl group. So if you are taking RCOH there, we get the product there is what? RR and not RH. Okay. Now substitution reaction the hydrocarbon part. First halogenation reaction. What carboxylic acid having a alpha hydrogen are halogenated at the alpha position. So alpha hydrogen of carboxylic acid is replaced with halogen atom. So this reaction is known as what? L-Volhard-Zelinsky reaction. Now, real substitution. Aromatic carboxylic acids undergo electrophilic substitution reaction in which the carboxyl group acts as a deactivating in metal directly. So, you can also do what? Electrophilic substitution reactions here. But the product will get will be metal directly because CH group is a deactivating group. Although we have to note that we cannot do Friedel-Crafts reaction with carboxylic acid because why the catalyst we use there? What? Aluminum chloride is a Lewis acid. It gets bonded to the carboxyl group. So we cannot do Friedel-Crafts reaction with carboxylic acid. So that's all there is to discuss in this chapter. Thank you.